Hello students, in today's lecture we are going to learn about mechanical properties of solids. NCERT section 8.5.3 to 8.5.4. We will also solve an example 8.5. This is disclaimer. Learning objectives. By the end of this lecture, you will able to understand the concepts of bulk modulus and Poisson's ratio. So this is the index. So in today's lecture, we will cover first 8.5.3 bulk modulus. After that, we will solve an example 8.5. And last, we will see 8.5.4 Poisson's ratio. So let's start. Here, our aim to understand the concept of bulk modulus. So let's start by looking at what happens when a body is submerged in a fluid. The fluid applies pressure equally in all directions on the body, which we call hydraulic stress. This is the same as the hydraulic pressure acting on the object. This hydraulic stress causes the volume of the body to decrease, leading to what we call volume strain. Volume strain is defined as the change in volume divided by original volume. We can say volume strain is equal to delta V divided by V. Here delta V is change in volume and V is original volume. Both are measured in cubic meters. Alright, delta V measured in cubic meters. Original volume V also measured in volume cubic meters. So think about it. What will be the unit? So we can say strain. Volume strain itself has no units. It's a unitless quantity. Alright. Formula for the volume strain helps us quantify how much the object is compressed. Now let's define bulk modulus. Alright. So bulk modulus is the ratio of volumetric stress to volumetric strain for a material. The figure here shows how applying pressure from all sides, from vertically downward, vertically upward, towards left and towards right. So how figure shows how applying pressure from all sides reduces the volume of an object. So bulk modulus tells us how much a material resists uniform compression. Materials with a high bulk modulus like metals don't compress easily. Yes or no? While those with a low bulk modulus like rubber compress more. So it depends on the material. I hope this is clear. So now mathematical formulation. The formula is B equal to minus P divided by delta V divided by V. And you know, P is the increase in pressure and delta V here, delta V is the change in volume and V is the original volume. Alright, so the term delta V divided by V is the volumetric strain. Yes or no? And P is the increase in pressure. So remember, pressure is measured in pascals and strain is a ratio, so it has no units. It's a unitless quantity. Here, the negative sign indicates the fact that with an increase in pressure, a decrease in volume occurs. So that is, if P is positive, if P is the positive, delta V is negative because the object is shrinking. So for a system that's in equilibrium, the value of the bulk modulus B always comes out positive. This is because the negative sign in the formula cancels out the negative change in the volume, giving us a positive value for B. This positive value tells us how resistant a material is to being compressed. If we talk about the SI unit, so we can say SI unit of bulk modulus is the same as that of pressure, Pascal or Newton per meter square. Alright, this makes sense because bulk modulus measures how much pressure is needed to cause a certain change in volume. Now we will understand the concept of compressibility. So relationship between compressibility and bulk modulus. So here question arises, what is compressibility? So we can say uh, compressibility, which we often represent with the letter K, small k, is defined as the reciprocal of the bulk modulus. In other words, K equal to 1 divided by B, where B is the bulk modulus. This means that if a material is very stiff, high bulk modulus, its compressibility will be low and vice versa. So mathematically, compressibility K is equal to 1 by V. In other words, we can say the reciprocal of B. So here, if we look, see it mathematically, so K is equal to minus 1 divided by P into delta V divided by V. Alright. So this is the compressibility. For example, if you increase the pressure on a material and its volume decreases by a small fraction, this formula tells you exactly how compressible it is. So we are continuing the concept of bulk modulus. So now let's look at the bulk moduli of the some common solids as shown in the table 8.3. Bulk modulus, represented by the letter B, measures how much pressure is needed to compress a material by a certain amount. So here is a table listing the bulk modulus values for several solids: aluminium, brass, copper, glass, iron, nickel, steel. Alright. So bulk modulus here for several solids measured in the units of 10 to the power of 9 newtons per meter squared, also called gigapascals. G, capital G or PA. Here capital G means giga and PA is the unit Pascal. Alright. For example, aluminium has a bulk modulus of 72, or we can say 72 into 10 raised to the power 9 Newton per meter square. Alright. And while nickel is much higher at 260, look at here, 260 nickel, this one. Alright. This means nickel is much more resistant to compression than aluminium. I hope this is clear. So material, liquids, water, ethanol, carbon disulfide, glycerin, mercury, and gases, air at STP, standard temperature pressure, and their numerical value of bulk modulus. So bulk modulus measured in the units of 10 raised to the power 9 Newton per meter square. So water has a bulk modulus of 2.2, while mercury is much higher at 25. For gases like air, the value is extremely low because of the order is 10 raised to the power minus 4. Alright. So let's analyze what is the table is showing us. First, notice that solids have much higher bulk moduli than liquids. This means solids are much less compressible. Next, liquids themselves have much higher bulk moduli than gases. This means liquids are much less compressible than gases like air. Now, uh, to understand the concept of bulk modulus, so let's start with solids. So solids are hard to compress, all right, because their atoms are tightly packed and strongly connected to each other. All right. So this is the arrangement of the particles in solid, liquids, and gases. So we can say uh, solids are tightly packed. All right, and comparatively liquid are less, and more comparatively gases are more less. So now let's look at liquids. Here, liquids can be compressed a bit more than solids because their molecules are still connected, but not as tightly. So in the figure, you can see that the particles in a liquid are close together but can move around each other. This is why liquids can change shape to fit their container. Gases are the easiest to compress because their molecules are loosely connected and far apart from each other. This is why gases can be squeezed into a much smaller volume. So let's examine table 8.4. This table lists the various types of stress and strain, the corresponding elastic moduli, and which states of matter they are applied to. So look at here. Here is the table. This one, type of stress: tensile or compressive, shearing, and hydraulic. Right. So here, stress: two equal and opposite forces perpendicular to opposite faces, whereas strain: elongation or compression parallel to the force's direction, delta L by L, longitudinal strain. So shape, change in shape, yes, and volume, no. Elastic moduli formula is this one, all right, and states of matter: solid. Similarly for shearing and hydraulic. So the table here explain about the stress. This will help us understand why bulk modulus is unique, since it applies to all three states: solids, liquids, and gaseous. Example 8.5. Average depth of the Indian Ocean is about 3000 meter. Calculate the fractional compression delta V by V of water at the bottom of the ocean. Given that the bulk modulus of the water is 2.2 into 10 raised to the power 9 Newton per meter square. Alright, let's see the solution. So let's start by listing all the information given in the problem. So first, the average depth of the Indian Ocean is given as h is equal to 3000 meters. This is the vertical distance from the surface to the bottom. Second, the bulk modulus of water is B equal to 2.2 into 10 raised to the power 9 Newton per meter square. Acceleration due to gravity G equal to 10 meter per second square. And density of water rho equal to 1000 kg per meter cube. Pressure at the depth of ocean is given by P equal to rho GH. And substituting the values, we get pressure is equal to 1000 kilogram per meter cube into 10 meter per second square into 3000 meter. So solving this, you will be get P equal to 3 into 10 raised to the power 7 Newton per meter square. Alright. Now let's recall the formula for bulk modulus. So B equal to minus P divided by delta V divided by V. Alright. So here we know P is the increase in pressure and delta V change in volume, V is original volume. And the negative sign shows that an increase in pressure causes a decrease in volume. So rearrange the formula to solve the fractional compression, which is delta V over V. So the absolute value of delta V over V equals pi equals to P divided by B. Alright. Now substitute the values and calculate. So the pressure at the bottom is calculated as depth times uh, density times gravity, and we have already found that to be 3 into 10 raised to the power 7 Newton per meter squared. So the fractional compression delta V over V is pressure divided by bulk modulus. So after calculating, delta V upon V is equal to 1.36 into 10 raised to the power minus 2. Alright. Now solving the fractional compression. So fractional compression means the change in volume divided by the original volume, written as delta V over V. This tells us how much the water is compressed under the pressure at the ocean's bottom. So delta V upon V is equal to 1.36 into 10 raised to the power minus 2. This means that the volume of the water at the bottom is reduced by the about 1.36% compared to the surface. So to convert into percentage, multiply by 100. So here delta V divided by V, mode of delta V divided by V is equal to 1.36 into 10 raised to the power minus 2 into 100. So solving this, you will be get in terms of percentage. So it will be 1.36%. This means that the even under extreme pressure, water volume decreases by just a small amount. Alright. Now Poisson's ratio. So now let's define Poisson's ratio. It measures a material's tendency to deform in directions that are perpendicular to the direction of the applied force. For example, if you stretch a rubber, alright, if you stretch a rubber band, it not only gets longer but also becomes thinner. In simple terms, Poisson's ratio tells us how much a material narrows or widens when we stretch or compress it. Imagine pulling on a piece of clay As you pull, it gets longer but also thinner on the sides. According to physics, Poisson's ratio is defined as the ratio of transverse strain to the longitudinal strain. Alright, here longitudinal strain, or we can say axial strain. In other words, it's the amount of sideways lateral change divided by the amount of lengthwise longitudinal change. For example, if a rod stretches by 1% in length and narrows by 0.3% in width, the Poisson's ratio would be 0.3 divided by 1, which is 0.3. Now, uh, let's start by defining lateral strain. So basically, lateral strain is the strain or deformation that happens perpendicular to the direction of the applied force. For example, if you pull on a rubber band, it gets longer, but it also gets thinner in the middle. This thinning is due to lateral strain. So lateral strain is defined as the ratio of the change in diameter of the wire delta D to the original diameter D. Alright, so lateral strain is equal to delta D divided by D. Both delta D and D are measured in meters. So the strain itself has no units. It's a pure number like 1, 2, 3, 4 without unit. Simpson-Poisson. So Simpson-Poisson discovered that within the elastic limit of material, the lateral strain is directly proportional to the longitudinal strain. This means that as you stretch a material more, it gets thinner at a predictable rate. Alright. Now, uh, imagine a metal rod with an original diameter D, alright, and an original length L. When we stretch the rod, its length increases by an amount delta L and its diameter decreases by delta D. When you pull on something, it gets longer and thinner. Poisson's ratio is equal to lateral strain divided by longitudinal strain, and longitudinal strain is delta L by L. So Poisson's ratio is delta D divided by D and divided by delta L by L. So rearranging, you will get delta D divided by delta L into L by D. This form is useful if you know the absolute changes in the diameter and the length. Now, let's look at the definition. Poisson's ratio is the ratio of two strains, the lateral strain to the longitudinal strain. Yes or no? So, dimensions of the Poisson ratio, we can say dimensionless or unitless quantity. This means it does not have any units like meters or kilograms because it's a ratio of two quantities with the same units. So it's just a pure number. Factors depending Poisson's ratio. Poisson's ratio value depends only on the nature of the material. Right? So for steel, the Poisson's ratio that typically ranges from 0.28 to 0.30. This means that for every unit of length it stretches, it contracts by about 0.28 to 0.30 units in the perpendicular direction. And for aluminium, on the other hand, Poisson's ratio is about 0.33. This is slightly higher than steel. So aluminium gets a bit thinner when stretched by the same amount. So students, now towards the end of the session, we are looking at the summary of the today's lecture, bulk modulus. So bulk modulus tells us how resistance a material is to being compressed evenly from all sides. The formula for bulk modulus is B equal to minus P divided by delta V by V. Negative sign in the bulk modulus formula ensures B is a positive quantity, as an increase in pressure causes a decrease in volume. Compressibility is a reciprocal of bulk modulus. So K equal to 1 by V is equal to minus 1 by P into delta V divided by V. Solids have significantly higher bulk moduli, lower compressibility than liquids, and which in turn have much higher bulk moduli than gases. Solids are hard to compress due to tightly packed atoms. Liquids are more compressible and gases are easiest to compress due to loosely connected far apart molecules. Bulk modulus is applicable to solids, liquids and gases, unlike Young's modulus and shear modulus, which apply only to solids. Lateral strain is the strain perpendicular to the applied force, defined as delta D divided by D, where delta D is the change in diameter and D is the original diameter. Poisson's ratio is the ratio of the magnitude of lateral strain to the corresponding longitudinal strain, expressed as a Poisson's ratio delta D divided by delta L by L, or we can say delta D divided by delta L into L by D. Remember that the Poisson's ratio is always dimensionless and has no units. Its value depends only on the material itself, not on the size or shape of the object. Now we have some practice questions. First, a material undergoes a pressure increase of 5 into 10 raised to the power 6 Newton per meter square and experiences a volumetric strain of minus 0.002. Calculate its bulk modulus. Water has a bulk modulus of 2.2 into 10 raised to the power 9 Newton per meter square. If a volume of water experiences a pressure of 1 into 10 raised to the power 5 Newton per meter square, what is the fractional change in its volume? Why does the bulk modulus formula include a negative sign? Explain the physical significance. A cylindrical wire of length 50 cm and diameter 0.5 mm is stretched by 1 mm. If the change in diameter is 0.001 mm, calculate Poisson's ratio for the wire material. And last, a rope of an original length of 20 meters is stretched, resulting in a longitudinal strain of 0.0005. What is the change in the rope's length? Alright, so these are the practice questions and these are homework for you. Alright, thank you for your attention.